Welcome everyone, nice to meet you again. Today we are going to learn activation functions, part 1. Upon completion of this video, you will be able to understand what an activation function is and the 3 types of activation functions, which encompasses binary step function, linear function, and nonlinear functions. You will understand the merits and demerits of each function, and get familiar with their graphs and derivatives. Finally, you will also learn the relation between sigmoid and tangent h functions and their derivatives. You will see that sigmoid is essentially a rescaled version of tangent h. An activation function is a very important concept in neural computing. In biological neural networks, we have learned that neurons have an electrical potential, which is a voltage difference between inside and outside of the cell. A neuron has a resting potential and an activation potential. When a certain threshold is reached at -55 millivolts, the neuron will be activated and fire an action potential. To mimic this biological process in the artificial neural net, we introduce the notion of an activation function to decide whether a neuron should fire an action potential. Specifically, an activation function is a mathematical function attached to each neuron. It determines the output of a neural network, that is, whether the neuron should be activated or not, based on whether each neuron's input is relevant for the model's prediction. Moreover, for multi-class classification problems, an activation function can also help normalize the output of each neuron. The concept of the activation function is not new to us. In previous sessions, we've already seen it. For example, in a perceptron model, after we calculate the weighted sum for all the inputs, a binary step function is then applied to the weighted sum z to produce a binary output y. Here, the heaviside step function h is a simple example of the activation function, as it decides the firing of a neuron based on whether the weighted sum z is positive or negative. We can replace the step function h with a more general function f. Thus, the output y is represented by f of z. Here, f denotes an activation function. Z is called pre-activation value, meaning that z is the value before applying the activation function. The output y is called activation value. Apart from the binary step function, there are also a variety of other activation functions. Linear function is another simple activation function, which takes the following form: Lx equals c times x, where c is a constant factor specified by the user. Unlike the step function, whose output range is a binary value 0 or 1, the output range of the linear function is a scaled real number that is proportional to the input. This is a major advantage over the step function. However, the disadvantage of the linear function is also obvious. Its derivative is a constant value c, showing no relation to the input value x. Thus, it is impossible to use the gradient descent method to train the neural net in the backpropagation through this linear function. Now let's see a simple example on how to predict the output of the neuron using the activation function L of x equals 2x. Note that here, in the right half of the cell, we draw a line to denote its activation function is a linear one. We first take the weighted sum z, which is 2. Then we apply the linear function L to 2, which yields the output 4. It is worth noticing that when c equals 1, the linear function is also called an identity activation function. A linear function is easy to compute, but in practice, we rarely use it in neural networks. This is because the linear combination of the linear functions is still a linear function. This property implies that a linear activation function would make all layers of the neural network collapse into one. For example, let's consider the following neural network with 3 cells. The activation function for each cell is a linear function. Without loss of generality, we take the constant value c to be 1 in this example. Now let's predict the output y. For the first neuron, the weighted sum is w1 times x. Since the activation function is an identity function, the output of this neuron is w1x, which will be used as the input of the next neuron. For the same reason, the output of the second neuron is w2 multiplied by w1x. The output of the third neuron is y, which is w3 multiplied by w2 w1x. We can see that despite 3 layers, the effect of this neural network is equivalent to the following single neuron. In this neuron, the output y is w times x. When we set the weight w to the product of w1, w2, and w3, the output y becomes the same as the 3-layered neural network. Thus, the linear activation function would make all layers of the neural net collapse into one. To overcome this problem, we introduce nonlinear activation functions, including sigmoid, tangent h, and ReLU. First, let's look at the sigmoid function. This is the definition of the sigmoid function, which is 1 over 1 plus e to the minus x. The graph of this function is like a snake. It is an S-shaped function having smooth gradient. The range of the sigmoid function is between 0 and 1. The main advantage of this function is its smooth gradient. In comparison, the step function has a sudden jump at 0 for its output value. As a result, for binary classification problems, we can see that the perceptron using a step function can only decide whether each data point is in one category or the other. All the points within the same category are labeled with the same value, 0 or 1. This classification result cannot tell how far and how close each data point is to the separator line. In this example, we can see these 2 points are very close to the separator line. Unlike the step function that can only label them with 0 or 1, the output of the sigmoid function shows the probability of each data point for a particular class. For example, we can see the 2 data points close to the separator line have the sigmoid output value around 0.5, while other points far away from the line exhibit high or low probability for the particular class. Thus, sigmoid functions are widely used for binary classification, better than step function. The second advantage of the sigmoid function is that its output value is normalized between 0 and 1. In contrast, the output of a linear function can be any real number with no boundaries. Consequently, when a linear function is applied to binary classification, its output doesn't show the probability of each data point for a particular class. There are two horizontal asymptotes for the sigmoid function. From the graph, we notice that when x is very large, the output tends to y equals 1. When x is very small, the output approaches y equals 0. Mathematically, we can readily verify that when x tends to positive infinity, the exponential of minus x approaches 0. Plug in this into the sigmoid function produces sigma of x approaches 1 over 1 plus 0, whose result is 1. Similarly, when x tends to negative infinity, the exponential of minus x approaches positive infinity, leading to the denominator of the sigmoid function being extremely large. Thus, the sigmoid function approaches 0. Based on the above two cases, we see that for very large or very small x, the limit of the sigmoid function is a constant value, implying that for such large or small x, the derivative of the sigmoid function tends to 0. This is called vanishing gradient problem, which will result in the network refusing or being too slow to learn further. This is the first advantage of the sigmoid function. To make this clearer, let's depict the derivative function of the sigmoid. We see that the two ends of this function approaches 0, which is consistent with the fact that the slope of the sigmoid curve at two ends tends to 0. The second disadvantage of the sigmoid function is that its output values are not zero-centered. To address this limitation, another nonlinear function called tangent h is invented. We will introduce it shortly. The third disadvantage of the sigmoid function is a high computational cost. This is due to the existence of the exponential function in its formula. From the graph, we also observed that the maximum value of the sigmoid derivative function is much smaller than 1, leading to its output range being very narrow. This is another disadvantage of the sigmoid function. Before illustrating this problem, let's first take a look at the derivative of the sigmoid function. We show the following theorem. The derivative of the sigmoid function is the product of the sigmoid function times 1 minus the sigmoid function. To prove this, let y be the denominator. We can get the following two equations. Sigma equals 1 over y, and y equals 1 plus e to the minus x. Taking the derivative on both sides of the first equation produces the derivative of theta equals minus 1 over y squared. For the second equation, we take the derivative on both sides with respect to x. Since the derivative of 1 is 0, and derivative of e to the minus x is minus e to the minus x, it follows the derivative of y equals minus e to the minus x. Then we multiply these two equations together to get the following result. Since dy is cancelled out, the derivative of the sigmoid function equals 1 over y squared times e to the minus x. Then, using this equation, e to the minus x can be rewritten as y minus 1. Plugging this result, we can rewrite the derivative of sigmoid function in terms of y. Based on this equation, we can replace y with 1 over sigma. Then, the derivative of a sigmoid function can be rewritten in terms of only the sigma itself. Simplifying this expression produces our final result. Pictorially, this theorem can be depicted as follows. The blue curve is the sigmoid function, and the green curve is 1 minus sigmoid. The two curves are symmetric about y-axis. Since their ranges are between 0 and 1, multiplying them together will produce a squeezing effect on the final result, which is the derivative of the sigmoid function. We see that before squeezing, the value of the sigmoid and 1 minus sigmoid functions at x equals 0 are both 0.5. Multiplying them together produces 0.5 squared, which is 1/4. This is the maximum value of the derivative of the sigmoid function. Mathematically, this maximal value can be obtained from this expression. If we use a and b to denote these two terms, in light of the inequality of arithmetic and geometric mean, we have the following result. In the denominator of this expression, sigma plus 1 minus sigma equals 1. Thus, the final result is bounded by 1/4. Here, the equality sign is attainable whenever sigma equals 1 minus sigma. That is, sigma equals 1/2, which is consistent with the graphical result. Note that this maximal value, 1/4, implies the vanishing gradient issue of the sigmoid function. Because the size of the arrow is reduced by at least 75% at each layer in backpropagation, which limits the ability to update the weights. It is worth mentioning that this theorem provides a fast way to get the numerical gradient of the sigmoid function. For example, if we've already know the value of the sigmoid at x equals 2 is 0.88, we can directly use this formula to compute its derivative at x equals 2, which is 0.88 times 1 minus 0.88, with no need to compute the analytical expression of the sigmoid derivative function first. As we will see shortly, this theorem will be very useful in backpropagation. The second nonlinear activation function is tangent h, whose expression and graph are as follows. We can discern that tangent h is also an S-shaped function, having smooth gradient, which is similar to sigmoid function. Unlike sigmoid, whose range is between 0 and 1 and not zero-centered, tangent h is a zero-centered function, whose range is between -1 and 1, which is symmetric about x-axis. Moreover, the maximal value of the derivative of tangent h is 1, as opposed to sigmoid function, whose derivative is maximally 1/4. Thus, the size of the arrow of tangent h function would not be substantially reduced by at least 75% for each layer. However, tangent h also suffers from vanishing gradient problem. For very large or very small inputs, the slope of tangent h approaches 0. In addition, tangent h is computationally expensive due to the existence of the exponential functions. It is interesting to note that several tangent h properties outlined above are quite similar to those of sigmoid. This is because these two functions have the following close relationship. That is, tangent h of x equals 2 times sigmoid of 2x minus 1. Graphically, this expression indicates sigmoid is a rescaled version of tangent h. We can see that this green curve is a sigmoid function. After rescaling and translation, it becomes a tangent h curve whose range is zero-centered. To mathematically prove this relationship, we can start with the definition of the tangent h expression. Multiplying by e to the minus x on both numerator and denominator produces the following result. We now use a trick by replacing this 1 with 2 minus 1 first, and then splitting this fraction into two parts. The first part can be rewritten as 2 times sigmoid of 2x, and the second part becomes -1. Combining these two terms together produces the final result. Using this rescaling formula, we next show the derivative of the tangent h function is 1 minus the square of tangent h of x. To prove this result, we first employ the rescaling formula to express sigma of 2x in terms of tangent hx. Then we take derivatives on both sides of the rescaling formula. We notice that the derivative of sigma of 2x is 2 times the derivative of sigma of x. Thus, the right-hand side becomes 4 times the derivative of sigma of 2x. Since the derivative of sigma equals sigma times 1 minus sigma, thus the following result holds. Finally, we replace sigma of 2x with this expression in terms of tangent h of x, which yields the following result. Simplifying this equation produces our final results. Throughout the proof, this equation is worth noticing because it implies that the derivative of the tangent h function is a rescaled version of the derivative of sigmoid. Graphically, we can see this curve is the derivative of sigmoid. After rescaling, the derivative of tangent h is derived. Looking at the changes in the peak of the curve, we can see that the maximal value of the derivative of sigmoid is 1 over 4. During rescaling, we multiplied by 4, which produces the maximal value 1 for the derivative of tangent h function. Today, we have mainly covered linear activation functions and 2 nonlinear activation functions, sigmoid and tangent h. In the next session, we will learn more about other activation functions. That's all for today's session. Thanks very much for your watching. See you next time.